mini computers in the entire world. And while it looks terribly complicated, it's actually based on a very simple idea. A processor and some memory linked by a single data stream. That's a structure known as a von Neumann machine, and it's pretty much the way every computer in the world is built, including the micro you have at home. But they're not all like that. Meet a non-von Neumann machine, non-von 1, built here at Columbia University. It ran for the first time in January of 1985. Looks a lot simpler inside, and that's because it's based on a totally different type of computer architecture called parallel processing.
Parallel processing is an attempt to get round what's called the von Neumann bottleneck. Modern transistors, the calculating part of the computer, can perform quite complicated functions in a billionth of a second, but it could take 10 times longer for the result to be passed along the wires, even though it travels at half the speed of light. Of course, one answer is to make the wires shorter.
Well, there's one critical problem with that, and that is heat. These elements that we now use that get these superb switching speeds also tend to dissipate a tremendous amount of energy. And when you compound that by cramming them all into a tiny amount of space, you can wind up with so much heat generated that unless you're very clever about the way you design your refrigeration system to go along with the raw machine, you wind up heating up those chips to the point where they don't work anymore. It turns out that silicon has a fairly narrow operating range of temperatures, and very quickly you wind up with something too hot to be practical. So in fact, the latest supercomputers really are very small, very highly efficient refrigerators.
The non-von answer relies on the fact that the processors, the chips containing the transistors, are now the cheapest part of many computers.
The machine that we're building right now, the non-von supercomputer, has a very large number of processors, each of which in fact is comparable to a small personal computer of the sort you might have at home. One important difference is that we have a lot more of them, each of whom can get instructions from the outside and have a little bit of local memory to store, say, a data element at a time and then process it independent of what anyone else is doing.
This independent processing, or processing in parallel, means that a problem can be broken into a number of components, each of which is solved at the same time and therefore faster. But there are some fundamental problems with this approach.
Probably the single most important one is communication. How do we get a machine designed in such a way that these different processors can talk to each other all at the same time and effectively and coordinate their execution of all these different pieces of the problem? That's the single hardest problem.
Connecting even a few processors together so that they can all talk to each other soon becomes unmanageable. So in non-von, the processors are organized in several different ways.
One of the key structures is what we call a binary tree, which is something that starts out with one processor up at the top that has two children, as we call them. Each of those have two children, and so on down to the bottom.
At present, non-von has only 64 processors, each on a separate chip. But the most recent development here is to put 8 processors configured in a tree format on a single chip. And eventually, they hope to have up to 1 million processors in future machines.
It's very exciting. The raw figures we get are absolutely astounding in terms of the amount of computational bang that you get for the buck. I don't know if that's an English expression, but what you get in terms of cost performance. But on the other hand, the basic problem that people may have is that if they got used to programming in Fortran or in C or in Pascal or a language like that, they may find the kinds of techniques that we use to be very foreign.
The non-von uses a parallel version of the programming language Lisp, and some types of calculations can be speeded up 100-fold.
Suppose we had a business and we were trying to raise the salary of everybody in the sales department by 10%, but not raising anybody else's salary. We would store each employee record in a separate processor, and then there would be a series of instructions, each of which would be executed simultaneously by all of the different processing elements, but on their own employee record, that might say something like this. You could start by saying, take a look inside your department field. If it's not equal to sales, then turn yourself off temporarily and don't listen to what I'm about to say. Then the next set of instructions would say, multiply your salary field by 1.1. And at the end of that set of instructions, all of the salesmen would have their raises. And then we send out another single instruction which says, now everybody wake up and start listening again. So that's a typical way that in a short fixed amount of time, all of those different processors have done something to their individual memory elements.
Non-Von is the culmination of 5 years' work here at Columbia University, but this is not the only place that parallel processing is being explored. In a number of schools around the country, alternative approaches are being experimented with, and more than one company is set to release an actual commercial parallel processing computer. The one thing that all the creators of these different approaches believe in common is that their machines are the machines of the future.
Well, Columbia University's Non-Von may eventually use up to 1 million 8-bit processors. Well, an alternative approach has been adopted by the Bristol-based chip manufacturer Inmos. They've developed a new device that they call the Transputer, a single piece of silicon with a powerful 32-bit processor, its own memory, and the built-in ability to link directly to other transputers. Phil Atkin has written some demonstration software for the Transputer. Phil, I really like your butterflies here. What are they showing?
It's a very simple demonstration, actually, just showing a pair of transputers talking to each other. We've got one transputer generating the images on this screen, one transputer generating the images on this screen. It's not that simple, though. One of the transputers is generating a butterfly, which is flying between the screens, so that data is being transferred from one transputer to the other.
It's the blue one. There it goes. It's just switched
yeah.
over. But that doesn't seem to be showing much more than we're seeing on those two BBC micros.
It's not. We're using about 1% of the transputer's total resource. It's simply a demonstration of concurrency communication.
Now, can you buy this Transputer today?
You can indeed. You can buy this board, which will plug straight into your IBM PC. Here's the transputer, 2 megabytes of memory and interface logic to connect from the transputer to the IBM PC.
That's 2 megabytes of memory. How fast is it?
That's about 10 MIPS.
That's about 10 times faster than the ordinary IBM A2, which is the fastest IBM PC.
That's right. You can plug 5 of these into the A2, in fact, giving you 50 MIPS.
50 MIPS, I can't believe it. How much is really usable?
45, 46 is pretty good.
That's very impressive. How do you program it? What languages are you using?
Fortran, C, Pascal and Occam.
Occam. What is Occam?
That's the language we developed at Inmos to program multi-transputer systems.
Well, we used to Pascal, we used to C and Fortran. Why do we need another language, Occam?
Well, you can program a single transputer in C, Pascal, but bind the entire system together in Occam to create a multi-transputer environment.
Is it difficult to learn?
It's not difficult at all, in fact.
Good. Well, I'll come back to you later, Phil. We've also been joined by the marketing manager of Inmos. Welcome. Tell me, Chris, how much is it going to cost?
The particular board that we've just seen there, Mac, sells for £2,900, but for you, £5,000.
Oh, that's a real bargain. What about the chip itself?
The chip at the moment is selling for £420, but we expected that price, as with all semiconductor devices, to fall to around £50 over the next couple of years.
So that seems to be a good reason why I shouldn't buy one for 2 years.
Only if you want your competitors to get ahead of you, Mac.
So I should buy one now and really get to know how to use it?
Absolutely.
Do I get a copy of Occam with it? Does that come free?
You buy the Occam at a slightly additional price, the compiler and that for the AT all come together.
And I suppose I've got to pay twice as much for the Occam as anybody else.
Indeed.
Thank you very much. Tell me, how do you envisage it being used? What's the market for?
There are many applications for the Transputer that we're being designed in today, right from supercomputers through CAD workstations down to process control applications. One particular application that it's being designed into at the moment is the fingerprint project, which is being developed for the Home Office. In that system, the system takes and codes somebody's fingerprint and generates a 1 kilobyte image of that fingerprint. This is then distributed onto an array of over 1,100 transputers.
So that the actual image of the fingerprint is put in the memory inside the transputer itself?
Each transputer has a copy of that, and then the database from the Winchester is passed past those transputers, and they search then for the match.
And how big is the database?
Well, the database roughly at the moment is building up. There are 3.5 million criminals in this country, all of which have, say, 10 fingers, depending on their crimes. Each finger is a kilobyte, so we have 35 gigabytes of data that have to be searched. The system they're using today is based on some mini-computers and takes roughly 20 days, or would do, to search for that database, which is clearly impractical. With the transputer-based system, they can bring that down to a couple of hours. And by increasing, again, the number of transputers, you can get that down further.
So criminals, watch out. Where else do you see it being used?
The transputer is also very good for graphics applications. You can take a graphics image and break it up into separate parts and give each one of those parts to one transputer. Many transputers can then generate one frame, and many other transputers can then generate multiple frames, giving you real-time animated graphics.
Some of the stuff we've been seeing in the past is one giant computer just doing one particular screen and then filming it and making it look continuous. You brought some very nice illustrations of graphics along today.
We have.
Let's go and have a look at them. Phil, what have you got here?
I've actually got a very powerful machine here, 22 transputers working together to generate these images.
Slow down a minute. 22 transputers, is that 220 million instructions per second?
That's right, this is very powerful.
So that's the equivalent to 2,200 IBM ATs.
Yeah, I can demonstrate that, in fact.
Just to do a picture?
Just to do a picture. It's actually a very complex picture. It's the Mandelbrot set, it's a fractal. It's very compute intensive to generate this. About 6 hours on an IBM AT, and watch this. Very few seconds.
Now, just to repaint that screen would take 6 hours on
At least 6
IBM.
hours, something like 30 hours on the BBC Micro. We're about 7,200 times as fast as a BBC Model B here.
And each one of these lines here is actually being generated, by an independent...
by a different transputer, and they're being combined on the graphics system.
And 22 of them all intercommunicating. We can actually see it operating on a BBC Micro to see something and compare the actual things. There it is. It's slightly different colours. No, it isn't. Well, you can also cycle the colours on this, can't you?
I can, yeah, watch this.
Go on, go.
It's
doing a lot of calculations now. There it goes. Well, that's very, very pretty indeed. Thank you very much, Phil.
Fascinating. And that music produced on a Sinclair Spectrum